Hi everybody. I am very excited to announce our keynote speaker for this evening. Welcome everyone to iQuHACK 2022. This is Professor Mikhail Lukin of Harvard University. Professor Lukin's work focuses on quantum optics and quantum information, including seminal work in the development of atom and artificial atom-based quantum computing and networking. We're very excited to have you here tonight, Professor Lukin. So without further ado, please take it away.
Thank you, Madi, for the kind introduction. And I would like also to thank the organizers. This is amazing. So I wish I would participate, in this event myself. So I was asked to give a talk which would be hopefully broadly accessible and give a little bit of introduction to the field. So I understand that participants here include a wide range of aspiring quantum scientists, from high schoolers all the way to advanced postdocs. And with that in mind, I would like to start by just telling you a little bit about kind of what's going on in this field. Most of you have heard about this kind of term, quantum revolution. So in fact, it's now very hard not to hear about that. So it's almost, in the news almost daily. The question is, what's it all about? So in the first few minutes, I'd like to give you a sense, this all kind of starts from the notion that the information, its acquisition, storage, and transmission is fundamentally connected with physical devices, physical entities. And the progress in technology over the past couple of decades basically tell us that the ultimate elements of the sensors, processors, transmitters will eventually be of the quantum size. That means that, the information carriers will eventually be kind of on a scale of single atoms, single molecules, or maybe single photons. And one of the kind of driver of that is, of course, the famous Moore's law, which you can express in different terms. And one way to kind of look at it is how many atoms you kind of need to kind of encode a bit of information. And while people are extremely ingenious about kind of extending the life of this Moore's law, I mean, it's very clear that at some point, it will approach the limit where basically the bit of information will be stored in kind of in a device which is close to one atom size. And people already kind of a couple of decades ago started to wonder what will happen, in this case. Would it be a stop to this kind of, would it be a barrier to the progress? And in some sense it is. But then people also realized that actually you can use fundamental constituents of matter, such as single atoms, electrons, nuclei, photons, to acquire, carry, store, and process quantum information. And the important thing is that all those systems, basically, which live in a microscopic world, obey the laws of quantum mechanics. So what are these kind of laws? So these laws are actually, something that, we have been studying now for almost 100 years. There is ample evidence that they are the proper physical laws which govern the behavior of microscopic world. But at the same time, these laws are very counterintuitive. They are very surprising to us in everyday life. So for example, there are notions such as quantum superposition that basically is a statement that object can be in multiple places at once. So I guess there are people now from all over the world listening, so in principle, there could be an object which are in all of these places at once simultaneously, or kind of as indicated here, in this quantum world, an object can take different paths around, an obstacle, and these paths can undergo a phenomenon known as quantum interference. They can actually sometimes cancel each other, and can sometimes enhance each other. Even more counterintuitive is a notion of something called quantum entanglement. So this is basically this non-local superposition state, of the type that I just indicated. So for example, if an object is in multiple places at once, or all over the world, in this case, what will happen if you make a measurement in basically of this object in one location, it immediately tells you what the state, what the physical state should be in another location. And this is something which really puzzled people early on, whether such correlations can really exist, and it bothered famous people like Einstein. But actually, the experimental and theoretical work of the past century really tells us that these effects are real, and they're really taking place in a microscopic world. So the question which we are trying to ask and address is, can we use effects like this to process information, to enhance processing of information? And that's kind of the idea behind the quantum computer. So basically, quantum computer is a device which is capable of processing information by exploiting these fundamental quantum effects, such as quantum superposition, quantum interference, and quantum entanglement. So to build a quantum computer, you have to basically go away from the notion of classical bit, which is basically 0 and 1, and instead think about encoding information in a quantum object. It's often is called quantum bit. And the key property of this quantum bit, and that's why it's different from the classical bit, is that it can be in a superposition state. It can be, for example, in the state which we write as a superposition of 0 and 1 with certain phase relations between each other. So such a phase relation is basically doesn't make sense in the classical world, and in the quantum world, it is essential for the description of the state. Moreover, if we start with many quantum bits, what we can do is prepare the superposition of states, which are basically a combination of different quantum bits, if you want a combination of different input states. And remarkably, if we now take such an input state and put it in a quantum device, which undergo the evolution according to the laws of quantum mechanics, what will happen is that, this kind of amplitudes, associated with each of these component of this kind of state will actually undergo quantum interference, and that's kind of the mechanism which enables, which is something which is called quantum parallelism. So what is quantum parallelism at a very high level? This is what gives quantum computers their power. So for example, if you start with the register where the information is encoded in states of individual atoms, zeros and ones. And if you start with a fairly modest quantum computer, which has maybe about 300 quantum bits, so you can prepare states which involve these superpositions of these different combinations of zeros and ones, and basically kind of in the single state of the quantum computer, you can actually, in principle, simultaneously store and process more solutions than a number of particles in the entire universe. So this is, something which is, potentially clearly very powerful, because even to describe a state of this type, classically, you need, so much memory that you can just not, feasibly kind of attain with any classical system. What we'll see kind of later in this talk is that in reality, what give this quantum parallelism is what gives quantum computers their power. But in reality, of course, the situation is not as simple, because typically if you process all of these superpositions, if you make the measurement, you will only get out kind of one result, one outcome. So one has to, for this reason, one has to think very carefully about designing quantum evolution, designing quantum algorithms. And the way this is typically done is by using something which is called quantum logic operations. So this quantum logic operations is the quantum operations, which one should use to manipulate the qubits. And the two important notions here are the so-called single qubit rotation. So it's basically the way how you manipulate a two-state system. Oftentimes you kind of think about the two-state system as a kind of effectively a spin, basically kind of in physics, this corresponds to like a little, top, spinning top, which actually can point up, down, or anywhere else in a three-dimensional space. And indeed, this, using this kind of spin representation is something which is called block sphere. You can actually very effectively, parameterize the state of a single qubit, and basically you can understand how this state evolves in this kind of block sphere. And through this, you can actually define, kind of possible single qubit operations. And these are the things which you will likely use tonight and tomorrow. These are basically the so-called quantum gates, where you basically, one of the gate is, where you basically flip the qubit from one state into another. And you can flip it kind of either directly or with some kind of phase relationship, or you can just imprint the phase on the qubit. And these are basically these X operators, so-called X operators, Y operators, Z operators, Hadamard gates, the operation which actually creates a coherent superposition of these two states. In other words, rotates. This operation which rotates the qubit from this, from one kind of state, for example, 0, into a superposition of 0 and 1. In this case, superposition will, in this line, this XY plane. So these are all kind of fundamental components from which you can build quantum algorithms. But actually, single qubit operations is only part of the story. Another part is the operations which you need to create the so-called entangled state. So the great entanglement, which I already mentioned. So, and basically, this is done by these multi-qubit operations. And here are some examples of those operations. So these are the so-called control knot operation. Basically, the operation where depending on the state of one qubit, you flipped another state or not. Or controlled phase operation, sometimes controlled Z, called controlled Z operation, where you basically controlled on a state of one qubit, basically flip the phase of the second qubit. And there are few other operations which are also quite important. So all of these operations can basically create these superposition states, create these entangled states, and also they, for a given entangled state, by using them, you can also disentangle the state. You can basically take a complex state in principle and convert it into a state which of kind of individual independent qubits. So the quantum devices, which you will be using, would differ in that, what types of operations they can implement. So it turns out that if you have certain set of universal operations, you can then use them to create any other operation between the qubits. But I would like to kind of emphasize right away that these types of operations, the single qubit, two qubit, multi-qubit, and the manner in which they are implemented, for example, they can only be done globally, or if they can be done individually, serially or in parallel, determines what we often call a programmability of the device. How programmable is any given physical platform. So one other thing that I want to kind of mention is that, these are, like if you decompose your quantum evolution, in a sequence of gates, this is kind of, in a sense, very much similar to how the digital conventional computers work. In some other instances, sometimes you would like to actually run quantum devices more in an analog mode. And this is in particular interesting and important in the area of the so-called quantum simulator. So one of the kind of very original ideas behind or motivation to build quantum computers was that classically simulating quantum system is actually very hard. So, for example, if you just want to do the to simulate, exactly the dynamics of n-qubit system, you basically need to solve classically the to the n to the power n coupled linear differential equations. And actually, for n larger than something like 50 or 60 is actually very, very hard, essentially impossible to do. So, as an alternative approach, what one could do is one can implement kind of instead of doing simulations classically, one can take some building blocks, quantum building blocks, and try to assemble basically an analog model of the system that you would like to simulate. And so long as this analog model is programmable, you can basically try to through some standard set of operations kind of effectively try to emulate this quantum dynamics. And this can be done either completely analog way or completely digital way or somewhere in between. And so these are the other types of machines which actually are also playing very important role now in the development of the field. Okay, so with all of these building blocks, what are the applications, what are potential applications where quantum computers can be good for? This actually is a big question, open question in the field. But generally, as we will see in a second, quantum computers are actually quite hard to build. So you would like to use them only for problems which are fundamentally difficult, which are fundamentally challenging to solve. So basically, the types of problems where quantum computers have really a chance to play an important role are ever difficult problems which are can be solved, but with conventional method. But these methods are very expensive kind of brute force approaches which are very hard to scale, or some other problems which are basically impossible to solve with conventional methods. And so some examples of those is problems is basically problems which are more in the quantum simulation domain. So where you basically would like to understand the behavior or quantum dynamics of fundamentally quantum systems, such as, for example, understanding and designing new materials, or, for example, looking at kind of chemical structure and chemical processes. Some other classes of problems which people explore, however, are much more sort of conventional, classical computational problems, but are very hard problems. So, for example, problems involving optimization, where you have, in particular, combinatorial optimization, where you have, basically kind of a lot of frustration and very hard to kind of, figure out, what's a kind of most optimal solution is. So these are, for example, problems often, considered in computer science, such as, for example, max cut, maximum independent set. There are other, problems which are, for example, in number theory, and the most famous is perhaps factoring. This is a problem where actually, in fact, there exists an algorithm, a famous Shor algorithm, which allows you to factor in polynomial time, whereas a best classical algorithm should scale, known scales exponentially. But in this kind of landscape, what I put is actually a big question mark, and basically, myself and many of us in the field believe that the most kind of impactful, most interesting algorithms, still remain to be discovered. And what you see is that these algorithms, they kind of map, very naturally on the space of these different computational models, computational machines, which I already mentioned. So some of them will almost certainly require universal quantum computers, whereas, other could be potentially better solved or better suited for these programmable quantum simulators, where you basically build quantum dynamics, by hand to kind of emulate the behavior of the phenomenon which are fundamentally kind of non-classical. So that brings us to the point of building, quantum machines, which actually kind of very early on, almost 40 years ago, when people started figuring out that, some of these quantum machines can potentially be useful, was kind of considered, very removed, almost kind of ridiculous, notion and entertaining. However, 40 years later, we are now living in a very special time when there are now a number of platforms are kind of coming online, and actually, I would say in some way maturing, in which basically we can encode information, maintain quantum mechanical properties such as coherence and entanglement, and basically use some way to kind of program interaction and implement this logic operations and implement quantum evolution. So these platforms, some of them are illustrated here, that include ions, neutral atoms, atomic physics platforms, such as superconductors, photons, defects in solids. So in fact, I believe that at least two of these platforms you'll have a chance to actually play with, to kind of program and, and explore. And in fact, the third of this platform, defects in solids, will probably be a subject of tomorrow's talk by Professor Capellara. So with all of these kind of developments, where is the field? What are the key kind of outstanding, challenges? So let me kind of formulate it, try to formulate it in a simple way. So in my view, basically, the kind of the field is now at a point where it addresses something which I call ultimate quantum rivalry. And you could say, well, maybe it's a rivalry between different platforms or maybe between different countries. Actually, in my view, it's much more fundamental, because it really is a kind of competition between two different forces of nature. One of them is that, we would like to really control, have a full control over quantum systems. And basically, in all of these platforms, which I mentioned now on the left here, scientists can now control a system of few quantum bits and basically kind of prepare them, isolate them, prepare superposition, entangle, perform all sorts of quantum operations. And this is, in fact, what you will be doing over the next, 48 hours or so. But there is another kind of challenge, however, is that we would like to, while maintaining this control, we would like to scale the size of this quantum system. In fact, we would like to kind of scale it to the point where the number of qubits we control is, sufficiently large, potentially, a couple of hundred maybe or more, such that we can really kind of be well in a domain where you can just not simulate these things, classically. And so these are two contradictory forces of nature, controllability and scalability, which are present in many different aspects of human, activities, or in nature for that matter. But they are actually very much kind of at the center of this, of the effort, in the field of quantum information science. So what is the current frontier? So I would say the current frontier is really to kind of use this machine to start implement tasks which are beyond where modern classical computers have really a chance to compete. And typically this means that you need to have kind of well-controlled, well-programmable system of some number of qubits, 100 or maybe more. And then with these kind of machines, the hope is that we can really start basically using them as a kind of as in the early days of classical computers, and basically start encoding kind of some problems, start testing algorithms, and really try to understand what algorithms perform well, and what are the potential applications of these computations. And the second thing, what we hope to do with these systems is we hope to kind of learn from these experiments with 100 or so qubits to start kind of building bigger and even better quantum machines. So this is actually the frontier where I hope many of you who are listening to this talk will really be able to contribute. And some of these contributions can start, as early as tonight or tomorrow, whenever you can log in and start playing with this existing machines online. So what I'd like to now do is to kind of shift gears a little bit and tell you about one specific platform, which you will not be able yet to access in this year hackathon, but perhaps possibly the next year. And that kind of goes back to, again, to this pioneer in the quantum computing field, Richard Feynman, where, in one of the early lectures, he basically, hypothesized about making a computing device in which basically numbers are represented by a row of atoms, in which each atom can be in two states. That's the input. And then, basically he says, we now turn on interactions between these atoms, the Hamiltonian starts, ones move around, zeros move around, and finally, the particular bunch of atom, represents the answer, and it's basically measured. And what he said at this point, nothing could be made smaller and nothing could be more elegant. So inspired a little bit by this kind of famous quote, I would like to describe you what literally is pretty much realization of this Feynman's vision. So I'll talk to you about the kind of a new platform in which quantum processors are built based on arrays of neutral atoms. And before I go into kind of details, so I'd like to kind of have one page, summary of what atoms actually are and what are the atomic properties which are important. So most of you know that basically atoms, or all of you know that atoms constitute from the positively charged nuclei and basically negatively charged electrons kind of moving around them. And basically the energy of this electron motion is quantized. So basically there are certain states in which this electron can be. And for example, for hydrogen atoms, these states are characterized by the so-called principal quantum numbers. Basically, that's what's called M. And in addition to this kind of electronic energy states, the atoms have other properties. They have, for example, electrons have spin, nuclei have the degree of freedom called spin. And basically, as a result, these atomic levels, they basically split into these manifolds, and you can use now different degrees of freedom to encode a quantum bit. So in particular, one very popular degree of freedom, which actually is used both in neutral atoms and in ions, which you will be able to use over the next couple of days, is this spin degree of freedom, where you basically encode the information into this, kind of effective, angular momentum, or like a top, electron top, which can point up or down. Another way of doing that is to basically encode the information into the superposition of this kind of principal quantum numbers of actually different electronic orbital states. And in particular, what you'll see is that, we will be sometimes coding information in the superposition of the ground state, where the electron orbits very close to the center or to the core of the atom, and the so-called Rydberg state, when the electronic orbit is much, much larger. So kind of with that introduction, so I will now describe you the approach to building a scalable quantum system, which we use in our lab here at Harvard in collaboration with our colleagues at MIT and our startup company, iQuHACK Computing. So in this approach, the atoms are trapped in a vacuum chamber using focused beams of light, the so-called optical tweezers. So basically, this is a picture of the light beam, which is focused so tightly that it basically it creates some electric field here, which actually attracts the atoms to its focus, but it's focused very tightly, so it actually can attract at most one atom at a time. And what we do in our experiments, we start with large arrays of these focused light beams. We call them optical tweezers. And basically, on each given shot, we can basically load, a certain number of atoms. So basically, such a system, as you can, indicated here, has some entropy, so some of these tweezers are loaded with atoms and some are not, and we can actually get rid of this entropy by literally taking a picture of the system and basically removing the empty trap and then basically rearranging the rest in any desired configuration. And in that way, we end up with atoms which are spaced by, a couple of micrometers to each other. So they basically not talking to each other. To make them talk to each other, we excite them into this so-called Rydberg states, into the states where electron orbits, in a large orbit, and the effective size of the atom greatly increases. And this is the mechanism for the to execute, for example, quantum logic operation. This is actually a collaboration between my group and the group of Markus Greiner at Harvard and Vlad Nguletic. So here is kind of some, images. What you see here are literally images of single atoms. And we prepare around 600 of them in this kind of square grid. And what you see is that basically this, you kind of can see the underlying square lattice here, but, the loading is clearly not perfect. So, but, if we do this, kind of dynamical rearrangement, we can create any kind of desired configuration. In fact, this, what you see now is a kind of slowed down compared to real time, but, this is basically a preparation of crystals, of artificial crystals of single atoms, and basically, here is, for example, if the slide advances, this is kind of an image of, perfectly filled 300 atom array. Kind of what's amazing is in the system, you can really, you're not limited to any kind of specific atom arrangement. So you can really kind of create any, arrangement of the atoms, basically any artificial crystal. In fact, you can create even the configuration of atoms where atoms are placed at random positions. Like, for example, you can program on a computer, this is where the atoms should sit, and then you basically, press the button, and here are the single atoms. So basically, the state of the art is we can now, as I already mentioned, create the systems composed from about like 300 individual atoms, so each trap, filled with probability of one more than 99%. So it's actually, there are some errors in preparation, but their probability is very small. So this, I should say, is something that is done actually by a group of amazing, students, and actually for some, for future, this will be actually relevant. So this actually is a kind of historical picture where, this is our group in the lab, on the day before the COVID lockdown started. And in the week leading to this COVID lockdown, so this the system, which actually now an laboratory experiment in our lab, has been converted to completely remote operation. It's now can be, programmed and operated completely remote. So as I already mentioned, we make atoms interact by exciting them into Rydberg atoms. And the reason why we like Rydberg atoms is that if you basically promote the atom into the state with with large principal quantum number, its size becomes very large. So basically, its size increases quadratically with principal quantum number. It can be easily factor of 1,000 or 100 more, or 10,000 more than the size of the ground state atom. So as a result, it becomes extremely susceptible to external perturbations like electric fields. And as a consequence, for example, two atoms, excited in the state, they interact very, very strongly with each other. So basically, the strong interaction can be used to enable something which is called Rydberg blockade. So I'll like explain it. It's a little bit technical, but I'll try to explain it. So the idea is simply the following. So if you take two atoms and try to kind of simultaneously excite them into this Rydberg states, if the atoms are far away, they will be excited independently and they will work independently. But if you bring the atoms close to each other, what will happen eventually is that these interactions will take over. And with the, for example, with the resonant laser pulse, which is used to excite atoms, at this point, you will be able to excite one atom or another, but never two together. And so that's the effect, which is called Rydberg blockade. Simultaneous excitation of two atoms is blocked closer to a certain distance. And this actually is a mechanism which we can use to entangle atoms, execute quantum logic in a very robust way, which is basically very insensitive to things like motion, position of the atoms, so long as they're within blockade radius. So basically, to summarize this kind of description, so this is a mechanism for high fidelity control of multi-qubit system, where we will prepare some arrangements of the atoms. First, these arrangements will be kind of non-deterministic, but then we'll move them around, prepare kind of regular array or desired arrays of the atoms, subject them to some laser pulses, and then eventually, what will happen is that system will undergo unitary evolution, and then we'll measure it. So using this approach, over last year, it was quite a remarkable year in many ways. We made a lot of progress in terms of realizing, both programmable quantum simulators, but also kind of gate-defined models for quantum computation. So these are some examples of the project. So we, for example, explored complex quantum phases in 2 dimensions. We studied tenon equilibrium dynamics, where you push the system from away from equilibrium. It starts evolving, entanglement starts growing. So I think it's very, very interesting regimes we can explore. So I'll mention, 2 projects today. One of them will be use this system as a programmable quantum simulator to realize topological spin liquids. And another one is kind of our effort to kind of build, actually quantum error corrected universal quantum computer. But, one can also use this system for other applications, for example, things like combinatorial optimization. And then last but not least, I should say that, our colleagues across the river here in Austin in a startup company called Quera, actually build a machine which actually is now, can be accessed through the cloud. And in fact, it will be publicly accessible later this year through AWS Bracket service. And perhaps this could be a part of the hackathon in a year from now. Okay, so let me just briefly, tell you about, 2 projects, which scientific projects, which we were able to do using this machine. So one project involves tackling a long elusive goal, realizing a very special state of matter called topological spin liquid. So this is a state of matter where basically the properties of the system is, is encoded in its topology, right? It's not kind of a conventional crystal where you can basically look at it and just see that, you have some local order, but you really have to kind of look at topological aspects of this. And this kind of idea has been proposed almost 50 years ago. And basically the kind of to maybe get a little bit of intuition, these states should actually emerge in the systems which do not favor kind of local order. So for example, if you have something like a system with antiferromagnetic interaction on this lattice, which is called frustrated. So antiferromagnetic means that spins, that the magnetic moments of atoms should be anti-aligned, and basically if this moment points down and this points on, where would this one point out? So you don't know to begin with. And actually that what happens in this kind of systems often, basically, do not order locally, but for that, they can develop this kind of topological order. They can, this magnetic moments can basically form these so-called dimers, which can then basically, cover the entire lattice. And in fact, the final state of the system, because of frustration, can be this superposition of all what's called dimer cover. So this is something that, maybe it's, kind of new for many of you, but at the same time, many of you have heard about things like Toric code. So this was a development, which started with the work of Alexei Kitaev about 20 years ago. And basically Toric code, it turns out, is an example of this spin liquid, and the property of the Toric code, which makes it very special, is that if you look locally, you don't see any kind of order. So what you need to measure are these kind of topological, loops or topological string operators, basically product of, Z operators or X operators within this kind of closed loops. And, because this encodes information in this kind of non-local way, that's actually the reason why you can potentially use it for topological quantum computing. But despite of all of this, great excitement, there was basically no conclusive evidence, of such states in any systems today. And over the last, 1.5 years, we actually, were inspired by our, theory colleagues who basically showed us how one could use this programmable Rydberg interactions to actually realize such state. And the idea is kind of very simple. So you need to start with the atoms which are positioned on this so-called frustrated lattice, where basically, it's a funny kind of lattice which is called Kagame lattice, and atoms should live on links of this lattice. And basically, if you excite one Rydberg atom and arrange blockade radius such that each atom blocks six nearest its nearest neighbors, it turns out that you can just map this kind of model into this so-called dimer model. And basically the prediction of our theory colleagues was that, the states which we should be able to create are this kind of superposition of all of this, the so-called dimer covering. So the way it's implemented experimentally is that we arrange the atoms on the desired lattice, engineer interactions between them, and then basically turn on our laser excitation, and then eventually measure the state. And this is a picture of this measured dimer. So it does look like one of these dimer covering, but what does it really tell us? It doesn't tell us much. In fact, if you look at any kind of global property of the system, what you see is that at the point where the theorists predicted that, we should enter into this topological spin liquid, we basically, reach some kind of plateau, but it's again, it doesn't really tell us, about, whether the system has topological order or something like this. So how do we actually measure this and probe, this kind of exotic states? So in order to do it, what we have to do is we have to basically, measure these kind of products of the operators, like in a Toric code, like products of the Z strings and, products of the X operators. And it actually turns out that it's possible to do. So in fact, the Z string operators are very easy to understand. It's basically, measuring that, just, tells us that, you created this kind of, dimer covering, right? So if you have a perfect dimer covering, that then, basically means that each of these kind of string has certain parity, and indeed we measure that is the case. But moreover, we can actually measure that this, with what we create, it's not just, some random mixture of this dimer covering, but it's a coherent superposition. That's what is being measured by this kind of string operators. What's actually perhaps most kind of intriguing is that already in this measurement, you can probe the topological properties of the system. And the reason how you do it, you basically look at the difference between closed loops and the open strings. And what you see is whereas the closed loops really show some signal, the open strings are dead zero. And it actually happens for both kind of X and Z strings. And, basically by doing that, you can really identify the onset of the spin liquid. So I think it's maybe a little bit too technical here, but basically, this is, you can define the order parameter and basically see that you have an upset of this quantum spin liquid phase. So, actually, this is a very exciting moment in this field, because basically this kind of ideas really allow us to, basically have unprecedented insight into topological matter. So it's kind of quantum simulators is really a new tool which is complementary to and more powerful than both analytical theories and numerical simulations. And basically what in particular is exciting is what we can start creating this kind of objects which are called anyons. They are basically very exotic excitations, in these systems, which can actually really be used to, for example, process and encode and process information in a way which is fundamentally fault tolerant. So I think I have maybe just a few minutes, so I would like to kind of close to wrap up. But before that, I'd like to show one more example. to kind of just demonstrate the power of this approach, and to be honest, also a little bit of cutting edge where this field is. So typically in the machines that you will be working with today, as well as conventional classical computers, what happens is that you basically make a chip, create some kind of architecture which has certain connectivity, and this is fixed at the point where the machine is fabricated, when it's designed. So I already showed you that in our approach, we can, arbitrarily position atoms, put them, anywhere we want. But actually, what's actually more interesting is that we can do that while preserving, quantum superpositions, or preserving coherence of the atoms. So how it's done in practice is it's done by encoding information into this so-called hyperfine state, basically spin states of the atoms, which I showed you already. And basically in this kind of states, the coherence can live very long time. The qubits can live for, actually up to a few seconds now. And just when we need them to interact, we will excite these qubits into the Rydberg states, into these highly excited states. And so the most remarkable thing is that once the atoms are in these protected states, spin states, they can be moved around, across the array while preserving quantum coherence. So here is an example. What we do here is we basically first create entangled pair of atoms by just executing controlled phase operations, and then just take these pairs and move them, far away from each other. And at this point, we can again, probe if they're entangled or not. And in fact, they are. And you see here, we basically did not lose any entanglement. So that kind of is the motivation to really start creating this type of architecture where you basically dynamically reconfigure the system. You create certain architecture, execute certain gates, store your qubits, move them around, execute certain gates, move them around again, and it proceeds. So to just illustrate it, I would like to show two examples. And one of these examples is something that you potentially will be able to explore this weekend in different platforms. And this is creating the so-called cluster states. So basically, cluster states are entangled states which can be used for various applications, including measurement-based quantum computing. And basically, to create a cluster state, what you need to do, you need to prepare first equal superpositions of all qubits, and then basically apply the controlled phase operations between each pair, or nearby pair of the qubit. So in our case, we can do it in literally just two steps. So in first step, we bring pairs of atoms together and basically do a controlled phase operation, and then move one atom relative to another, and then basically make another step. And then afterwards, we just read out these states in different basis sets, and then we can measure what's called stabilizers of this qubit. So this type of things is actually relatively easy to do. It doesn't, can be done in other architectures. And it's something that I encourage you to try, at least some of you over the weekend. But what you can immediately see is that our approach is not limited to this specific state. So in fact, in addition to cluster states, we can create, for example, things like STIN code, which is our correcting code. We can create a two-dimensional surface code. And perhaps what's actually most intriguing, and this will be, I would say, impossible to do with the current, well, any other current available system, we can create basically the states in free spatial dimensions. So how is it possible? Well, remember, we have a two-dimensional atom array, but this state, it's basically, in particular, we'll focus on the Toric code state on the torus. What we can do, we can unfold this torus, and basically it turns out that this Toric code state on this torus is equivalent to the graph state with non-local connectivity, or connectivity is indicated with the dotted lines here. So basically, what we can do now is we can use movable atoms. In particular, we'll use ancilla atoms, which we will think about as this kind of quantum head, similar to this magnetic head in old hard drives, which we will just move around the array of the data qubits to actually create this non-local connection, non-local entanglement. So in fact, we do it not just with one ancilla atoms, but with 8 ancilla atoms in parallel. And this is shown here. Again, the red circles here are control Z operations, which we implement in parallel. And then we eventually move this ancilla to this readout zone and basically read them out. So using this approach, we can create a toric code state on a torus, and basically to kind of, see that we actually have done it, we can try to encode qubits in this, because toric code is an error correcting code. In fact, because we are now on a torus, we can encode 2 logical qubits. One of these qubits will be encoded across one direction, and another one is encoded in another direction. In fact, what you see here, indeed, we can basically prepare the kind of both of the qubits in X state, and what's shown here is both raw measurement and as well as error corrected measurement. Because we measure all stabilizers, we can also correct them. One of them actually corrects to 1 all the way, and another one is a little bit worse. So basically, I hope you can really see that, this is kind of a very special approach, which can actually combine potentially both analog and kind of digital dynamics. And it's really a new, exciting kind of platform to explore, much more complex circuits and techniques. So I think I am at the end already of my talk. Maybe I'll just go to my final slide. So with this, I want to thank you for your attention, and also thank all the people whose kind of blood and sweat resulted in this work. And I'm happy to discuss if you guys have any questions. Thank you.
Misha, thank you so much for this awesome overview and some of the near-term applications that you have been working on recently. This was such a great talk. So we have a couple of questions from our participants that, if you don't mind, I would be glad to ask you. So the first question is, what kind of Hamiltonians can be generated in neutral atom arrays?
The Hamiltonians of the that we have generated so far were of the Ising type. But these Ising Hamiltonians with basically kind of programmable interaction and programmable connectivity. So it's easiest to generate the Hamiltonians which will have certain type of locality to them, geometric locality, but they don't have to be done in this way. And at the same time, it is also possible to extend this Ising Hamiltonians to generate, for example, terms which are, for example, exchange interactions. Basically, kind of these are much more generic spin Hamiltonians. There are other approaches where to this neutral atom quantum computing, where actually not only you can generate spin Hamiltonians, but also the atoms can kind of hop to each other. So in that case, you don't even you can't even think the atoms as a qubits. It allows you to implement even much larger range of models.
Awesome, thank you. The next question is, are topological logical states stable towards thermal excitations?
So this is an excellent question, and we'll answer the following. So they are predicted to be stable, and that's the reason why there is a lot of interest in the topological quantum computation. However, we have to see in practice to what extent they will be stable and robust. And that's kind of the main motivation for doing the experiments of the type that we do. So what we expect is that they will be certainly robust with respect to certain perturbation, but it's a question to what extent they will be robust to all perturbations. And for example, in our experiments, we see that we actually do have some anyons, and we are trying to understand how we can this kind of anyonic excitations on the top. And so basically what we are trying to understand, how we can kind of control these anyons, how we can maybe trap them, anneal them. So this is kind of very much the subject of ongoing research.
Thank you. We have a question about the main steps and challenges of going from the initial imperfect loading stage to the perfectly arranged lattice of neutral atoms.
What is that again? Sorry.
Yes, what are the main steps and challenges when you're going from the initial imperfect loading to the perfectly arranged lattice?
So basically the way how this procedure works, as I explained, literally is just basically you take a picture of the atoms and you realize, which traps are full and which are not. And then you kind of you basically kind of remove the empty trap and move the others in a way you want. So the key sort of things which kind of limit the performance of this. One is that you basically one is basically speed, and so you would like to do it reasonably fast, and for that you need to image atoms quickly, and it's basically at the moment it's a kind of a limiting step in our experiments in terms of speed, how quickly you can image atoms. So that's number one. The second is that you want to make these operations as parallel as possible, and that kind of requires some, very clever design of the pulses, and these are all now, remember, this control now is all in optical techniques. You have to design the beams, in the right way. And, then there are mundane things, like just, for example, the quality of your vacuum, and so basically, we believe that with the current approaches, we can certainly scale them up to, more than thousands of atoms, probably, to tens of thousands of atoms. But, we have to see, we have to do it before we can really, say.
Yes, that makes sense. Thank you for that. And I think Carlos has one final question for tonight.
Thanks, Misha, for the very nice presentation. I had a question for our participants. Basically, I wanted to ask you if you could have like ideas, or you would be particularly excited by which kind of applications if they could come up with, something that is maybe not researched much nowadays because maybe it's not so scientifically relevant or industrially relevant, but would be still something interesting that they could do in the hackathon.
Well, the question, the answer to this question is depends what kind of system you can, the scale of the system you can access, and basically depending on the size, I think there might be different avenues and different questions you can ask. So, assuming that you can access systems, and I don't know, you guys maybe should tell. Maybe I should have asked you how big are machines which are.
Yeah, well, so it's in the order of tens.
Yeah, so assuming, if you cannot access the system with like tens of qubits, I would say it would be most interesting to explore some kind of new avenues for things like quantum error correction, for redundant encoding. And, in particular, of course, there are these general theories of quantum error correction, which I think very useful as a guide. But then for any practical system, you realize, you will have certain imperfections, which will be dominated by certain kind of error mechanisms. And in this case, what you should really do is understand this error mechanism and try to, figure out a way, either through error mitigation, error correction, to basically kind of, circumvent them, to kind of generate the longest possible quantum evolution or extend the lifetime of the state, interesting quantum state, like, for example, small cat state, as long as possible. And that, I think, would be extremely interesting to explore on the machines which I learned.
That's great advice for the participants in the hackathon. I'm pretty sure they will get to work on that very soon. Thanks a lot.
Thank you, guys. And good luck to everyone. But I'm happy to answer still some questions. us.
Yeah, I think Maddie, if are you still there?
Yep. So yeah, thank you so much, Misha, for this great talk, and everyone, feel free to hang around on Slack tonight if you have additional questions. I know our friends from Microsoft and IonQ will be there to answer your questions, and then we'll see you online or on Twitch at 9 a.m. tomorrow to kick off the hackathon with our challenge announcement. So good night, everybody.